Have you ever stared into space, wondering what is out there? Wondering what exists far, far away? With visible light, we can only see so far. The Hubble Space Telescope can see about 13.4 billion light years away. Infrared telescopes, like the James Webb Space Telescope, can see even further at 13.7 billion light years away. In order to look at the furthest away light, you need to use microwave telescopes. As the universe expands, the light traveling within it gets redshifted or stretched out to longer wavelengths. The furthest away light we can see, known as the cosmic microwave background radiation, is from 380,000 years after the Big Bang. But wait, why can't we see all the way to the Big Bang? To explain this, let's start with a short summary of the Big Bang. The Big Bang began our universe about 13.8 billion years ago, when the universe started as a highly concentrated singularity. From this, the universe expanded. At an early point in the universe, the matter was so hot that the electrons couldn't stay attached to nuclei. This meant that the universe was filled with plasma, much like what makes up stars. With the electrons all floating freely everywhere, light was bounced and scattered about, making the universe opaque to light. As the expansion continued, the universe cooled, and eventually it cooled enough to pass the threshold of 3000 Kelvin, or the surface heat of the coolest red dwarf stars. At this point, the age of atoms began, and the electrons and nuclei bonded to make atoms in an event known as recombination. The universe was transparent to light for the first time, and the photons were free to travel. We now see these photons as the cosmic microwave background. But these photons are 3000 Kelvin, which would be red light, so why do we see them as microwaves? This is because the previously mentioned redshifting has resulted in these photons being redshifted to only 2.75 Kelvin. Why is this important? The CMB is one of the most significant pieces of evidence for the Big Bang. Since the further you look in distance, the further back in time you see, you need to know what happened early on to understand what exists far, far away. This is why, in 1989, the Cosmic Background Explorer, also known as COBE, was launched to test our Big Bang model with the cosmic microwave background. Not only is the existence of the cosmic microwave background a prediction of the Big Bang Theory, unlike other competing steady-state models, but the evidence seen from analyzing it comes in three flavors. They are the CMB's black body spectrum, which is a light that an opaque object emits due to thermal energy, the thermal map of the CMB, and the baryonic acoustic oscillations, which are waves in the plasma of the universe, much like sound waves, which are seen in the CMB. Blackbody spectrums are light spectrums emitted from an opaque object due to thermal energy. When recombination occurred, the universe became transparent to light, so the light emitted was directly due to blackbody radiation. The Far Infrared Absolute Spectrophotometer, FIRA's instrument of COBE, measured the blackbody spectrum of the CMB and got a set of data that greatly matches what our models say blackbody radiation for an object of a temperature of 2.75 Kelvin should be. The fact that they match so well gives our understanding of the Big Bang some merit in our understanding of blackbody radiation. Looking at the universe in both directions, we see galaxies of the same type and flavors. Overall, the universe appears to be very homogeneous in all directions. There is one question, however: how is the universe so homogeneous? If the light from these galaxies took 10 billion light years to reach us, then ignoring expansion, it would take 20 billion years to reach the galaxies on the other side. This is impossible, as the universe is only a little less than 14 billion years old, meaning that there has been no interaction between these matters at these distances. Early universe's isotropy, meaning homogeny, could explain this phenomenon, as similar initial conditions could produce similar results. Part of the Big Bang model includes a period of inflation, where in a very short period of time, the universe expanded many times its size, by a factor of 10 to the 26th in a fraction of a second, explaining the similarities across what are now vast distances. The homogeny can be seen in the map of thermal fluctuations in the CMB. The temperature variations are extraordinarily tiny, with one part of the sky being, for example, 2.7251 Kelvin and another part being 2.7249 Kelvin, but roughly the universe being overall isotropic early on. This map was obtained by the differential microwave radiometer instrument of COBE. There's another question, however: how could a perfectly homogeneous universe create distinct areas of high and low mass concentrations, such as galaxy clusters and voids? Well, yes, the map of the CMB shows that the universe is at a large scale homogeneous. At a smaller scale, you can see that there are anisotropies, which are the opposite of isotropies. The anisotropies reflect slight density differences in the early universe. The uneven density means that, over time, gravity pulled more matter into the already denser areas of matter, leading to the large-scale structures we now see in the universe. If the universe were 100% perfectly isotropic, instead of primarily isotropic overall, the universe would now only be evenly spread gas, and gravity would cancel out, meaning there would be no large-scale structures. The CMB matching our observations of the universe in the present shows the importance of the time before recombination to the structure of our universe, and indicates to us that the events preceding recombination actually occurred, which is part of the Big Bang model. Baryonic acoustic oscillations are waves that travel through the matter of the universe. This occurred before recombination. In fact, it happened before the nuclei could even exist, when light had enough energy to turn into particle-antiparticle pairs, which then could turn back into light from colliding. These quantum fluctuations led to slight density differences due to Thomson scattering, leading to a battle between the forces of gravity and pressure. This caused back and forth pulses which led to waves much like sound waves. When recombination occurred, the waves stopped, and the matter was left in its uneven pattern, being the anisotropies we see in the CMB map. We can measure these waves by creating a graph of the temperature fluctuations at progressively smaller angles in the CMB map to use the ratio of the different maxima of the resulting graph to find the ratio of baryonic matter to dark energy. With this result, we get a ratio of 5% baryonic matter, 27% dark matter, and 68% dark energy. These ratios can be compared to obtain ones by looking at type 1a supernovas and the universe's expansion, which find that these values obtained match the ones we got from the CMB. Since the COBE mission, there have been two other significant missions to map the CMB. These are the Wilkinson Microwave Anisotropic Probe, WMAP from NASA, and the Planck spacecraft from the European Space Agency, ESA. The WMAP mission was launched in 2001 to measure the anisotropies that COBE detected to a much more precise level. Unlike COBE, WMAP was positioned at the L2 point instead of in orbit around the Earth like COBE. The L2 point is the second Lagrangian point, where gravity of the Sun and Earth allow the orbit of WMAP to keep up with the orbit of Earth. While COBE had only an angular resolution of 7 degrees, 14 times larger than the Moon in our sky, WMAP has an angular resolution of as little as 0.25 degrees, 28 times the quality of what COBE had. This much larger resolution allowed it to create a clearer picture of the CMB than possible before. The WMAP mission obtained an age of the universe of 13.772 billion years. The Planck mission was launched in 2009 to measure the anisotropies in the CMB at an even greater resolution than the WMAP mission before. The telescope was also positioned at the L2 point and had an angular resolution of 0.17 degrees. This is 50% higher quality than what WMAP had and 42 times what COBE had. Planck had to have its detectors cooled down to as little as 0.1 Kelvin, as the precise instruments were very susceptible to interference by their blackbody radiation. The high resolutions of Planck allowed it to measure distortions in the CMB by galaxy clusters, helping us with observing gravitational lensing. The Planck telescope gave us an age of the universe of 13.82 billion years. The COBE mission is so important, not just because it helped certify predictions made by the Big Bang model, strengthening the model itself, but also because its CMB measurements made cosmology a precise science. Before we mapped the CMB, cosmology had a lot of theoretical backing, but not much direct observations. But now there are observations to back up our predictions. Now, we have the existence of the characteristic radiation of the Big Bang, the isotropy of the universe on a large scale, the anisotropies of the universe on a smaller scale, and measurements of baryonic acoustic oscillations to back up the Big Bang theory, leaving it to be our best explanation of the origins of the universe to date. These pieces of evidence match the events that the Big Bang theory predicts in ways that competing steady-state theories could not, such as recombination and light becoming particle-antiparticle pairs. These contributions to cosmology are why, in 2006, the Nobel Prize for Physics was awarded jointly to John C. Mather and George F. Smoot, who led the COBE mission.